All right, let's look at the definition of differentiable. A function f is differentiable at a if f prime of a exists, and we say it is non-differentiable at a if f prime of a does not exist. So remember that that definition of a derivative is based on a limit, so we need to make sure that as you're approaching that value from either direction, you're going to be going towards the same number. So there's several ways that a function can be non-differentiable at a point A. So we talked about this one in the last section when you have a corner like this, where it's just a very tight, it's an actual corner, so it's not a curve, but it's an actual, it comes to a point. And that's because if we're looking at the limit as we're approaching it from the left-hand side, you can see that's going to be a positive number. The limit as I approach it from the right-hand side is going to be a negative number, so those are not going to be the same, and you need to have the limits be the same for this to exist. So that's why we say, so f prime of a is undefined, and we say it's because it has a corner. Sometimes you're going to hear it as a cusp. I just say a point. Or a peak, I think is what I mean. Discontinuity, so here this is a discontinuity because you can see, remember when we learned about continuity, this is called a jump discontinuity. And again, because as we approach this from the left and from the right, we're getting different values for that limit. And so the limit as we approach A does not exist. And then a vertical tangent comes into an issue as well, because we'd have the derivative function would end up creating a vertical asymptote there. So when we've got a vertical asymptote, those are also undefined. So all three of these situations are when you're going to have an undefined, at those points, the derivative function is undefined. So a corner, any type of discontinuity, and a vertical tangent. So remember, we've got the different types of discontinuity, the removable, the infinite, and the jump. Determine the values of x for which the function f of x is non-differentiable and state the type. So we can see here that this is going to end up being, let's see, so let's actually go first to this discontinuous. I'm going to skip to letter B. So where is this discontinuous? So that's going to be here. We can see at x equals 1, we're discontinuous. -1. It's a jumped discontinuity. All right, but if we're trying to figure out where is this non-differentiable? So, all right, so we said if there's a corner, it's non-differentiable. We said that if there's a discontinuity there, it's discontinuous. And we said if there's a vertical tangent, it's discontinuous. All right, so when I look here, I see right off the bat we have a corner at x equals -3. So it's not going to be continuous there. I also see that the function itself is discontinuous at x equals -1. So that means that the function is not differentiable there. I have another issue when I am at +4. At +4, we've got a corner there. And then we actually have an example of the infinite right here, a vertical tangent. So you'd have a vertical tangent here. So it's also undefined at x equals -4 because of that vertical tangent. So again, if you go back to that last side, there's 3 ways that you can tell if a function is non-differentiable. So that's if you have a corner, discontinuity in the actual function itself, or a vertical tangent. So we found all of those spots. We had a vertical tangent here, we had a corner here, and a corner here, and we had discontinuity right there.